Have any questions for me regarding is there a small test available today? I mean, I can give you a small test if you want to, but according to the plan, we don't have a small test. See, we stick to the plan. The test that you just have is the quiz 2. That will be enough. I did not prepare any mini tests, but it's kind of easy to do. If you want me to give you one, I can give you one, no problem. Just say yes in the chat, and that means I'm going to give you one, inshallah. Since I'm guessing I'm not going to see many yeses, so yeah, keep going. So no, we don't have planned, actually, that's why. We have a quiz, we have one assessment per week, and we just had quiz 2, which is enough for this week, inshallah. However, for the next week, we are going to be having the topic that we're going to be covering today, the primes and greatest common divisors, are going to be part of this mini test next week, which is going to be just the week before the winter break, and then we're going to take a week of break, and then we come back and continue with chapter 6 and these parts, having a mini test every week again. So yeah, that's what I thought. No yeses in the chat. So no one wants a quiz, so no one wants a mini test. Yeah, so today, actually, see, I updated it from here as well. So let's dive in if you don't have any questions, which is kind of, okay. So today what we're going to be doing is actually define what are primes. Primes, and probably these things, you know them. Also the greatest common divisors, the least common multiples. You've seen these. The Euclidean algorithm, actually, this is also one of the things that actually, even though it's mentioned here, it's not part of it, actually, because it is not part of what we're going to be talking about. And this is one of the reasons why, actually, this was left out, the Euclidean algorithm. Okay. Okay, we talk about it. Okay, let's talk about it. I thought I removed it, but I didn't. Okay. So let's leave it. All right. I thought I had to, I removed it, but I did not, so let's keep it, no problem. So let's start talking about those primes. What are they? Well, you know some of those, but I just would like to make sure that we talk about them. And the main idea is that there are some numbers that have some properties that are very interesting, and these primes are one of those numbers. So what are those primes? Well, primes are integers greater than 1 first, so 1 is not going to be included as a prime. And so it is a prime only if the only positive factors of that integer p are 1 and p. What does this mean? That means that if you have a number greater than 1, right? So we don't want to include 1. So if we have a number greater than 1, and that number, if you try to divide it by any other number, you can't, because it can only be divided by 1. When I say divided, means the rest is going to be 0. What is remaining, let's say if you divide it by that, the rest of the division is going to be 0. That's what I mean. So when I say that 5, if you divide 5 by 1, well, it's possible. So you're going to have 5, and then the rest is going to be 0. So the rest is 0. That's what I'm talking about. Now, 5 is an example of a prime, because you cannot divide this by 2 and have 0 as a remainder, what remains, or by 3, or by 4, or by any other number. Now, if you go beyond 5, obviously, it's not going to be possible. It's going to be 0 point something. So a prime number is a number that you can divide by either 1 or that same number. So what are the prime numbers? Well, of course, we said 1 is not one of them, so we're not going to include 1. But we have 2. I mean, the prime numbers, I mean, smaller than 10 are 2, 3, 5. Why didn't I include 4? Well, 4 is not included because I can divide 4 by 2, which is going to give me 2 plus 0 in the remainder. So 2 divides 4, and we said that to be prime, I can only divide it by 1 on itself. So that means 4 is not an option. That's why I'm not going to say that 4 is a prime. 4 is not a prime. Okay, what about 6? Well, same thing. 6 is not a prime because I can divide 6 by 2, and I can also divide 6 by 3. And all this is going to give me 0 in the remainder. So 6 is not a prime. What about 7? Well, 7 is a prime. What about 8? 8 is not because I can divide it by 2. What about 9? 9 I can divide it by 3. And these are the prime numbers less than 10. Because 10 also is not going to be acceptable because I can divide it by 2. I can divide it also by 5. And the remainder is going to always be 0. So these are the primes. So the definition of a prime is that it's a number, an integer greater than 1, that is divisible either by 1 or itself, nothing else. If it's not the case, if it's not prime, we call it composite. So a number, an integer that is not prime is called composite. For example, 4 is a composite, 6 is a composite, 8 is a composite, 9, 10, and so on. So this is the definition of a prime. Now, how do we know? How do we find out if it's a prime? Well, there are different ways, and we're going to see some. Let me just move on. Now, there is, after we do these, we defined what a prime and a composite is, I would like to make use of those primes. Now, how do I make use of them? Is that every number, and this is the fundamental theorem of arithmetics, this one over here, it says, this theorem number 1, what it says, every number, integer of course, greater than 1, can be written uniquely as a prime, either because it's a prime, so this is only a prime, or a product of 2 or more primes, where again the prime factors are written in an order of non-decreasing size. Non-decreasing size means increasing, so non-decreasing, that means it's increasing. So let's have a look. Let's say we have this number 100. Now I would like to find out what are the prime factorization of 100. Well, basically what I have to do is to come up with, try to divide this number by the primes. So what are the primes? We've said that 2, we have 3, we have 5, we have 7. These are the ones that we've seen. But actually we can keep going and then find that actually there's 11, and then 12 is not because I can divide by 2, and then 13 cannot be divided by 2, cannot be divided by 3, by 5, by 7, by 11, and etc. So we can, how do I know if it's a prime or not? All I have to do is try to find out that if I can divide it but whatever is before it, and if I can, that means it's not a prime. But if I can't, that means I can only divide it by 1 because every number is divisible by 1, and then by itself. That's how we can find those primes. Now, what this theorem claims and says, actually not claims, it says that I can represent every number. Think about any number. Let's take a small number just to make it easy. Let's say 24. Every number, I can represent it as a factor, as a product of 2 or more primes, either as a prime or as a factor of 2 or more primes. For example, if I say 5, well, I can say that 5 is going to be 5. That's it, and that's all I have to have. It's just either as a prime, which is in this case, or as a product of 2 or more primes, and this is the case that I'm going to try to do. So here, 24. This is 2 times 12, right? Then I'm going to say, okay, 12 is 2 times 6. And then again, what is 6? Is 2 times 3. And which is going to give me like 2 to the power of 3 times 3. which is actually, this is a product of, as you can see, primes, and they are in an increasing order. So it's within an order of non-decreasing size. So that means the primes are keeping increasing. So that's the idea. Every number, I can represent it as a set of primes, a product of primes that are increasing, or as a prime itself, if this is the case. Now, how do I know? Well, basically all I have to do is to try to find out all the primes and divide them, the primes smaller than that number, and then divide them, try to divide this number by all those primes. As long as I'm able to find that the remainder is 0, that means I can include that as the product. Now, some of you may ask, okay, 641, that's a big number. Am I going to start from 2, 3, 7, and 5, 7, etc. until 641? Well, yeah, but I'm not going to ask you this. This is just for illustration purpose. So if it was in a question in the mini test or something, I'm not going to ask you about that. Something I'm going to make it easy to just do it manually, easily within like the reasonable time. But the idea is that this is how we can find out all the products of like this number, any number. So look at any number, all you have to do is to divide that number by the primes that are going to continuously increase until you reach that unique way to represent that. Is that okay? I don't know if there was, I heard something, I'm not sure if I had questions or no. All right. So the idea, to summarize, the fundamental theorem of arithmetics, what does it say? It says that every number can either be represented as like the prime, because that number is a prime itself, or a product of increasing primes. Now notice that this product is going to be a prime squared, for example, or cube, or to the power of 10, whatever it is. It doesn't matter, but it's a prime that is the multiple multiplied. I mean, that has like this to the power of any numbers. That means I kept dividing this number by 2 10 times, and it was always giving me the remainder is 0. So that's the idea. Now there is another theorem that says, okay, if I'd like to find that list of primes, what's the biggest prime that I can have in a composite n? If a number is composite, like if I know that, for example, this is a composite, I would like to know, okay, what is the biggest prime that I'm going to reach? Now, the rule says is that, this is the theorem, the theorem says, if n is a composite integer, then n has a prime divisor, which is, I can divide it by one of these numbers. Now, I can divide it by a number that is less than or equal to square root of that number. So what does it mean? Let's go back to this 100. Now, if I say this theorem, what does it say? It says that if I'm looking to find the prime products of the 100. Sorry, I want to find the product of the primes of that integer 100. I know, that theorem says that I know that the biggest prime is going to be smaller or equal to this, which is, in this case, 10. So I know it's going to be smaller than 10, or equal to 10. That's the maximum. Of course, it cannot be equal to 10, because 10 now is not a prime. So it's going to be smaller than 10. That's what it says. Because square root of 100, right? It's same as square root of 10 times 10, which is going to be 10. So that's what it says. And we can see now that actually it's always going to be the case. So if you'd like to just try it, I'd like to, just for out of curiosity, let's try that. So if I'm looking for, now I'm going to test it with this 999, which is going to say, what is it? So 999, what's the square root of it? It's going to be 31.60 or something. So because we're talking about integers, that means I'm pretty sure that it's going to be less than 31 or equal to 31. That's the biggest. Is it? No. The square root of 999 gave me 31.60. And I just said that the biggest number is has a prime divisor less than or equal to this. Then n has a prime divisor less than or equal to that thing. Well, look here. What I have here is that we said square root of 999 is going to be 31.60. 31.6, for example. And now I have something that is 37. Now there's something wrong, right? Can you spot the problem? Now in my case here, number is 999, and it says that 999 has a prime divisor less than or equal to square root of this, which is 31.6. Is that true? Knowing that this is going to be equal to 2 times 3 power 3 times 37 based on what is written here. Isn't there something that doesn't make sense? I'd like you to be more than just watchers. Okay, give me what's going on. What's wrong here? Do you see what I'm talking about? I want you to write something, talk something, do something. What's wrong in what I just said? In this theorem, and what I just shown you. If n is a composite integer, then n has a prime divisor less than or equal to square root of n. And we tried it with 100. It seemed to work because square root of 100 gives me 10, and we found that here all of them are less than 10, but here not all of them are less than 31.6. So what's the issue? It's not less than. Well, I still don't understand. What's the issue? What's the problem? There is a problem, obviously. Now, I want you to pinpoint what the problem is based on what you understood. Okay, there's a lot of silence here. I'm not sure if you're following or you're too confused. Okay, let's just read the theorem 2. What does it say? If n is a composite integer, then n has a prime divisor less than or equal to square root of n. Does it say that then n has all prime divisors to be less than or equal to square root of n? Is that what it says? Are we asking about that means every single one of them has to be less than square root of n? Or are we just saying that it has a prime divisor less than square? That means one of them, for sure, is going to be less than this number. So this theorem does not say that every single one of the numbers of these primes is going to be smaller or equal to this square root of this number. This is not what we're saying. We're saying that there is at least one. We know that if it's composite, at least we will have one that is smaller than or equal to this number. So that's what we're saying. So don't get confused. What we're talking about is that if there's a number like 999, composite integer, then n has a prime divisor less than or equal to square root of 999. That's in this case is 31.6, which is, we have 3. 3 is smaller than 31.6. So, and just to make it as an int, is more than 31. So yeah, this theorem works. It's just like the way I presented it was wrong. My mistake was saying that I was saying that every single prime is going to be smaller than this square root of 900 of that n, if n is this number here. So that was the problem that I wanted you to spot. So we could have bigger, yes, but the theorem doesn't talk about that. The theorem says that there is at least one that is smaller or equal to this square root of n. So just be careful. When you read something, just try to go into the details. All right, so now to make use of this, okay, for example, this theorem, let's show that 101 is prime. Now to show that 101 is prime, do I have to check all the numbers from 1, 2, 3 up till 101? And see, this is the idea. By using this square root of n, all I have to do, if I'd like to know that if a number is composite, is that I need to find the square root of that number, and then, so this is going to be obviously 10 point something, so I don't care about the point something, so I need to find that there is at least, I can divide it by, so this number, if it's composite, that means I can divide it by one of the numbers that is smaller than 10, one of the prime numbers that is smaller than 10, and if I'm not able to, that means actually, because I said that at least it should have one that is smaller, then this number is not going to be composite, because I cannot find any number that can divide it that is less than 10. So that's the idea. So the only primes not exceeding square root of 101 is going to be 2, 3, 5, and 7, because 101 is not divisible by 2, by 3, by 5, or 7, because 101 of each of these integrals is not an integer. So the quotient, yeah. It follows that 101 is prime. So what does it mean is that I'm using this theorem to find out that I just need to use a small number of primes to test if that number is prime or not. That's what I said. If I cannot find, let's say I'm doing like this 97. If I cannot find square root of 97 is going to be what? Just to have an idea, 97 square root is going to be 9.8. So let's say 9, because we're talking about integers. So it's going to be something about 9. So I need to find any number that can divide this, any prime that can divide this number, and that prime should be less than 9. In this case, I have 2, 3, 5, and 7 again. And if I can say that 97 is divided by 2, no. Is it divided by 3? Well, 9 plus 7, you know this rule, right? It's 16, which is equal, it's also going to be 1 plus 6, it's going to be 7. That's not a multiple of 3, so I know that this is not going to be divisible by 3. Do you know this rule? That actually have a number, whatever number is, you give me any number, and I'm going to tell you that if it's divisible by 3 or not, by just summing all the digits. And if the answer is going to be a digit with 2 digits, for example, or 10 or 12 or whatever it is, so let's say, for example, we have 5 plus 5 plus, this is going to be 11. 11, I'm just going to add this 1 plus 1, is going to give me 2. So this is not a multiple of 3, so I'm going to be pretty sure that I cannot divide this by 3. And you can just try that if you don't know this rule. Actually, this is something that is actually, I don't know how to prove that. Let me put it by divide by 3, as you can see. 1, 2, 3, 5 divided by 3 is going not to give me something without any remainder. So yeah. Anyways, the idea is, if I said 97, I'm trying to find that if I say that this is what are the different prime products of this 97, all I have to do is I need to find out that at least it should have something that is like smaller or equal to this 9. Now, of course, 9 is not a prime, which means it's going to be 2, 3, 5, or 7. So how do we know that? Well, let's try. Can I divide this by 2? I said no. Can I divide it by 3? No. Can I divide it by 5? It's no. How about I divide it by 7? So if I divide it by 7, 97, divide by 7, it's not going to give me no remainders. That means 97 is not composite. So this is going to be telling me that because the theorem says that if it's composite, I should have at least one prime divisor that is less than or equal to square root of n. I did not find that, which means that number 97 is going to be prime. And now if you'd like to test it, I mean, maybe also we can make use of those tools and list all prime numbers less than 100. Let's see. So if I have that, you can see that 97 is one of them. So anyways, I just want to make sure that we understand that, yeah, I need to come back here, to understand this theorem properly and we don't get it wrong. Okay, another example, find the prime factorization of this. Basically what we have to do is we start with this number and try to divide by 2. We can't, because dividing by 2 will have some remainder. And then 3, all I have to do, and then 7 plus 0 plus 0 plus 7, that's going to be 14. 1 plus 1, that's 5. 5 is not a multiple of 3, so it's not going to be divisible by 3. We can also prove it like this. Divided by 3, it's just going to be, see, there's a remainder. Now, oops. So we said this, I'm not going to divide by 2, not by 3. What about by 5? Well, obviously it's not something that has some 5 and zeros, so it's not going to be divisible by 5. Now how about 7? Well, obviously I can see that 7 is going to be 7 times 1001. And then I need just to keep going. Next I need to divide by the successive primes beginning from 7. What are the other primes that are 7? Well, we know that after 7, 12, we have 8, no, that's not a prime. We have 9, not a prime. We have 10, not a prime, because it's all of these I can divide this one by 2, this one by 3, this one by 2 and 5. And 11 is one of the primes. So can I divide this by 11? So 1001 divided by 11. I can, it gives me 91. So that means this is going to be 7 plus 11 times 91. And then let's find out 91. Well, obviously I don't need to have to divide them by 2, 3, 4, because if I was able to, I would have already. So I'll just keep going and increase. Now what's the next prime? 12 is not a prime because I can divide by 2. I can divide also by 3. And then 13 is 1 because I can divide by 2, by 3, by 4, so by 3, by 5, by 7, by 11. All these are not working. So by 13, let me try now. 91 divided by 13. Oh yeah, it works. So it's going to give me 7. Actually, I should have done something else. I forgot, because you see, I did not. I should have divided this by 7 again just to see. This 1001 divided by 7, I would have actually got another thing. So this is something I made the mistake of not doing. What I should have done is that I should have also, once I divide by 7 and it worked, I need to also divide this by another 7 and see that, okay, 143. So I keep dividing by 7. Maybe there's actually, you can divide it many times by 7 until I can't. Oh, so I cannot divide by 7. So let's bring it back how it was. Now divide by 11. Yes, I can. And this is going to be actually equal to 7 squared times 11 times 13. Because this is, if you divide by 11, we get 13. And this is actually prime, and this is going to give us those prime factorization. So 7007 is going to be 7 squared times 11 times 13. So this is how I can do that. So the mistake that I did is that as soon as I divided by 7, I assumed that it's this whatever the other number is not going to be divided by 7. So I should have actually tried to divide it multiple times by 7 until I find out that I can't. Then when I can't, I just go to the biggest prime number. So this is the process here that leaves us with that. Is that okay? I'm not sure if everything is fine. All good. Only one person says it's good, so we will assume that everybody says good. All right. Okay, you can do something if this is maybe hold on, what is it? If you're just too lazy for typing, you can just do this. Let me see this one here. Just thumbs up. That means okay, good. So you don't have to even write something. Anyways, I'm trying to just send. That's fine. So yeah. Okay. Now there's this the sieve of Eratosthenes. That's a kind of weird name, but I'm guessing this is the person. This guy is maybe the person who found out this way how to find all prime numbers not exceeding some kind of integer. Now let's say we have I would like to find all the prime numbers between 1 and 100. I'm not going to be using the GPTs or the Google search, whatever, because now Google search also uses the GPTs. So what I do, the sieve of Eratosthenes is doing this. It lists all the numbers from 1 to 100. And then I start with the prime that I know. And then what I need to do is I'm going to go for this 2, and then I'm going to, like in this case, underline or maybe strike. I can strike through every single multiple of 2, which means 4 is going to be gone, 6 is going to be gone, 8 is going to be gone. So this way I'm just going to pretty sure that because I can find that these numbers are multiples of 2, they are not going to be prime. Because we said the prime is going to be divisible only by 1 or itself. So I can find divided by another number. That means this is not going to be prime. So this is the idea behind all these underlines here. So we do that for 2. And then I'm going to do the same thing for 3. Now I'm keeping the same underlined ones. And then now for 3. Okay, that means for 3 I'm going to remove 6. 6 is already removed, but you see that's why they have 2 lines here. The first line when we struck 6 because of the 2. Now we struck it again because of the 3. And then we strike now 9, that was not struck before. And then 12 twice because it's 2 and 3. And 14, 15. So all these are removed because they are not going to be for sure prime numbers. And we're going to keep doing that until when? Well, again, until this we know that until the square root of 100. If we cannot find that is one that is smaller than or equal to the square root of 100, then basically it's not going to be needed to do that. So for us it's going to be up to 7, right? So for here that means I'm going to do the same thing for 3, the same thing for 5, the same thing for 7, and what I'm going to be left of are the numbers that are not going to be struck any time, and these are the prime numbers. And you can see 7 and then 11 and then 13, and these are struck, and then 17 and then 19, and then there's 23 and then 29. So these are all the prime numbers until smaller than 100. So the last one is this 97. So the sieve of Eratosthenes is just allowing us to find like a process how to find the prime numbers smaller than a specific number. So this theorem, that's theorem number 2, with the square root, it's very convenient because it allows us to actually find prime numbers kind of easily. Anyways, easily, it's not relatively easily. Is that okay? because actually basically that's half of what we have to see for today. Those prime numbers, so let's just summarize what we've seen about the prime numbers. So we decided that a prime number is a positive integer. Sorry, no. A prime number, what is it? Yeah, a prime number is a positive integer that is going to be greater than 1, and it can be only divided by 1 or itself. And that's what a prime is. Anything that is not a prime, which means I can find a number that is going to be divided by some other number, or have some other factors that are part of it. This is going to be composite. So we have either primes or composite numbers. And then we said that I can have, this is the theorem of arithmetic, the fundamental theorem of arithmetic, that says every integer greater than 1 can be written uniquely as a prime, like this, or a product of 2 or more primes, a product of 2 or more primes. So this is an example of as a prime. This is same thing as a prime. So a prime, but multiplied 10 times. Or product of 2 or more primes, like these ones. These two are pertaining to this, where the prime factors are written in an order non-decreasing size. Well, basically this is just something that is saying it's in increasing, which means the numbers are continuously increasing. Why increasing? Because this is how we find them. We just start with the smallest primes and then divide until we go to the biggest ones. And now we know that we don't have to go until the last one before this to know if it's actually, for example, for this case, I don't have to try them all. If I do the square root of 641, what is going to be the square root of 641? Is 25 point something. So all I have to do is to try to divide by 2, 3, 5, 7, 11, 13, what else we said, 14, 15, 16, 17, and then 18, no, 19, and then 20, 21, no, 22, 23, 24, and 25. All these are going to be 24 divided by 2, 25 divided by 5, so up to 23. So all I have to do is, if I can try to divide this by these numbers and I can't have any remainder to be 0, that means I don't have to keep trying with the more than prime numbers more than 23, because I know that if I don't have anyone smaller than the square root of this, that means for sure it's not going to, I'm not going to find anyone else, any other one. So that's the beauty of this theorem number 2, which is if n is composite, then n has a prime divisor less than or equal to the square root of n. And then the last thing we've seen is this the sieve of Eratosthenes, which is just if you'd like to find the prime numbers smaller than some kind of specific positive integer, all we have to do is to list the numbers from 1 to that specific integer. So we'd like to find the prime numbers less than or smaller, less than or equal to that number, and then we just remove the ones that are divided. Notice it's very important to not remove the first one. See, for example, the 2, I'm not removing this one because it would be a mistake. I need to keep 1, the first one, and then I'm going to remove any others that are multiples of the 2. And then I do the same for the 3. I leave the 3, and then I'm going to go for the 6, for the 9, etc. So like here, 6 and 9, 12, 15, 18, etc. And then same thing with 5. So with 5, we're just going to keep this first one, and then the 10, the 15, 20, 25, 30, 35, and so on. And same thing for the 7. So we keep the first one, it's just the second one that we just remove. And that's pretty much it about these topics of what we'd like to cover about the primes, inshallah. So if you don't have any questions, I'm going to move to this greatest common divisors, and the other thing is going to be the least common multiples. These two are kind of going together, but let's talk about the first one. The greatest common divisors, which are the largest integer that divides both of the two integers. So let's say you have like two numbers, and we'd like to know which number can be the biggest number that divides these two numbers. And that's the greatest common divisors. Now let's have a look at the definition. Let's a and b be integers, not both 0. So we don't want them both to be 0. The largest integer d, such that d, remember this, d divides a and d divides b. What does it mean? That means a can be divided by d and b can be divided by d. So is this d divides a and d divides b is called the greatest common divisor of a and b, and this is the biggest number that's actually going to be dividing these two, because we said it's the largest number. We don't want any number that divides the two. We want the greatest. Now let me just, for example, like for the sake of this example, let's just have 16 and 32. Okay, let me write them like this, 16 and 32. So what is the greatest common divisor of a and b? I'm not looking at one common divisor, because 2 is a common divisor. I can divide a by 2, so 2 divides 16, and then 2 divides also 32. But that's not what I'm looking for. I'm looking for, it's not even the 8. I'm looking for the biggest one. Okay, what's the biggest one that can divide both? So now we're touching, okay, how can I find it? Now how to find this biggest one? Okay, debug again. All right, not able to do anything. All right, okay, can I? All right, keep, no, discard. All right, what I was saying is 16 and 32. So this is A, this is B. Now how do I find the greatest divisor of the two? So all I have to do is basically find what are the prime factorization of these. So what's this prime factorization of 16? It's 2. We have this 16 divided by 2 gives me 8. Divide by 2 again gives me 4. Divide by 2 gives me 2. So this is going to be 2 to the power of 4. 2 times 2, that's 4, times 2, that's 8, times 2, that's 16. Correct? I'm looking for... so somebody says 8. All right. We'll look at 8. 8 is the common divisor. Okay, let's have a look. Now, what about 32? If I'd like to write 32 as the prime, what's the prime factorization of 32? I'm going to start by dividing by 2. That's 16, which means I can divide also by 2. That's 8. By 2, that's 4. By 2, that's 2, which is going to give me 2 to the power of 5, which is actually 2 to the power of 4 times 2. Why am I writing it like this? Because I would like to find the biggest common divisor between the two, and the biggest common divisor between the two is 16. Not 8, not 4, not 2, even though 2 divides both, but because according to here, I'm not looking for any integer that is dividing the two. I'm looking for the largest, the biggest one. So that's very important. So this is what this stands for. This greatest common divisor, GCD, is the largest integer such that that integer divides the first number, and that integer divides the second number. Is that okay? So it's important for you to get that, because you might get lost into thinking, oh, any number can be the common divisor. Yes, but we're not looking for any number. We're looking for the greatest. Looking the greatest common divisor. That's what we're looking for. So that's why we're looking for the largest integer. And again, we have this bug. I don't know what I'm doing wrong to make this bug. Okay, so let me see. So we'll present three methods. Okay, fine. So let's find out the first way how to do that. I mean, I obviously shown one way. So it's just to find the common divisors, the positive common divisors. What's the greatest between 24 and 36? So that's another example when we have 1, 2, 3, 4, 6, and 12. So what is this about? I'm just trying to find the numbers starting from 1, 2, 3. Why am I starting from 1 this time? I'm not saying that. I mean, the way that I said before, the example that I said just earlier using the prime factorization, actually I was not really accurate about that, because I don't need to do the prime factorization. All I have to do is try to find a number, whatever the number is. But actually the prime factorization, if you divide it by, if it's 4 is a multiple, that's obviously because it can use a prime of 2. But anyways, it doesn't have to be that, because this, maybe that's the more easier way, without looking at if it's a prime or not prime. All I have to do is to list all the numbers that actually are going to be dividing these 24. So that means I can divide 24 by 1, obviously, by 2, yes, by 3. By 3? Well, yes, 24 divided by 3, that's 8. Okay, by 4? Well, because 24 divided by 2, that's 12, divided by 2, that's 6. And then I have also 6. 6 times 4, 24. And the other one is 12. So this divides 24. What about 36? Well, also divides by 1, 2, by 3, because it gives me 36 divided by 3, it gives me 12, right? And 36 divided by 4 is going to be 36 divided by 2, that's 18, divided by 2, that's 9, so 9 times 4, 36, right? I'm just trying to follow all the same numbers, try to find the biggest. So I went to find the biggest, the greatest, the divisor of 24. I found that it's 12. I'm just trying to find out if this 12 is going to be the same. So I'm just following the same steps. 36 divided by 6, yeah, because 6 times 6, 36. And we said that 12 is not dividing 36, because 3 times 12 gives us 36. So 12, if we divide 36 by 12, is going to give us this 3. So because this was the biggest dividing 24, and actually it also divides 36, so we can say that the greatest common divisor between 24 and 36 is the 12. So the idea is we find all the common that are both common to 2, and then we look for the biggest one, and that's it. So that means we'll take the first one and try to find, okay, what can divide it? Okay, 1 can, 2 can, 3 can, 4 can, 5 no, 6 can, 7 no, 8 no, 9 no, 10 no, because it's 2.4, so I'm looking for when the remainder is always 0. 11 no, 12 yes. So and then I can go maybe 13, 14, but it's actually after 12 it's impossible to have something, because this is going to be 2 times 12, so anything bigger than 12 is going to be less than 2, so there's no way. So the only number that's going to be is 24. So that's another number that can divide this number here from 1, 2 until these are the possible divisors of 24. And now I'm doing again the same thing with 36. I can divide by 1, by 2, by 3, by 4, by 6, 7, no, 8, no, 9, 9. Well, yes, I can divide by 9. 36 divided by 9 is going to give me 4. 10, no. 11, 12, no. 13, no. 14, 15, 16, 17, 18. Well, 18 as well, because we said this divided by 2 gives me 18. And above that, the last one is going to be 36. Now, among all these numbers, what's the biggest that is in common between the two? So that's what this method of. I think it's not really well explained here, but this is basically what we do. We just find all the numbers that I can divide this number with, up until that number itself, but generally the number itself is anyways. And then once we find it, we just go for both of these, and then we just do the intersection of these two sets and find the maximum of these two, of that intersection. So in the intersection, it means I have this 1, I have this 2, I have the 3, and I have the 4, and I have the 6. The 9 is not in both of them, but that's it. So now, among all these numbers, which one is the biggest? That's 12. That's how I find it. So let's apply the same thing here. Well, all I have to do is then find the 17. Can it be divided by 1? By 2? No. By 3? No. 4, 5, 6, 7. Actually, this is a prime, so the only other number is going to be 17. Okay, what about 22? Okay, 22, I can divide by 1, by 2, 3, no, 4, no, because if I divide by 2, that's going to be 11, I can divide by 2 more. So, 4, no, 5, 6, 7, 8, 9, 10, 11, yes, I can divide by 11, and then anything after that, because it's going to be 2, so the last number is going to be 22. Okay, so that means among these, which is the highest common divisor between the two? Well, in this case, it's just 1. I hope that's fine. Is that okay? Thank you. What about the others? No, this, so okay. Great. Any questions? We'll keep going. All right. So the other method, actually, this is the one that I showed you just in the beginning when I said that. Okay, let's have the prime divisors and then find them. So because it is often important to specify that two integers have no common positive divisor other than 1, we have definition number 3. The integers a and b are relatively prime if their greatest common divisor is 1. Okay, so well, this is just to mention something special about those. Once we find those that are like this, any two numbers where the greatest common divisor is equal to 1, they're going to call them relatively prime, which means these two, the idea is that these two cannot be simplified. The greatest common divisor between these two numbers, if you have 22 times divided by 17 or 17 divided by 22, this is no way you cannot reduce that to anything else. It's going to stay as it is. While if you have, for example, 24 divided by 36, or the opposite, 36 divided by 24, it can be reduced by this common divisor. So that means this is going to be equal to, we said 3 times 12, and then this is going to be equal 3 times 12, 2 times 12, and then we can just, this is equal to, so you can simplify. That's what this greatest common divisor, actually, basically, one of the usage of that is how to simplify these divisions of numbers. So this relatively prime is a special case when you have two numbers, which basically what something is relatively prime if the greatest common divisor of these two is going to be equal to 1. That means you cannot find any other number that can divide these two by other thing than 1. And if you have a set of numbers, they are pairwise relatively prime if every two of them is the greatest common divisor is going to be equal to 1. So let's say if you have these three numbers and you want to know if they are or to prove that they are pairwise relatively prime, all you have to do is you have to prove that the greatest common divisor between 10 and 17 is going to be 1, which is going to be also the greatest common divisor between 10 and 21, and also the greatest common divisor between 17 and 21 is 1. So all different combination of these 10, 17, and 21. So these two, or these two. So we check them. All of these, they have this greatest common divisor to be only 1. So this is the sequence with all of this is what it means. And then the one that I actually started with, which is the prime factorization method. This one, maybe let's have it formally now introduced. So we were looking for this way, and now we can maybe have a look at this way how to write this, the minimum between the two. What does it mean? So let's say, for example, we have this prime factorization of 120 and 500. So 120, we assume that this is the prime factorization. That means 120 is equal to this. And then 500 is equal to this. Now, the greatest common divisor between this 120 and 500 is going to be what? Now, I have both of them have 2. So what I'm going to do, I'm going to take 2. And then here in the power, I'm going to take the minimum between 3 and 2. So this is what it says. The minimum between the, let me just write it better. The power is going to be the minimum between 3 and 2. Obviously, the minimum between 3 and 2 is going to be the 2. So let me write, this is going to be 2. Why? Because I'm looking for something that is in common. What is in common between these two in terms of the 2? This one has 3 2's, this one has 2 2's. That means this one has 2, 2, 2. And this one has only 2. So which one is in common? Obviously, they all have in common 2 times 2. So this is the 2 squared. This is what they have in common. So that's why this minimum comes from. So if there's something that is in 2 places, we're going to have them together. How about the 3? Well, they have, this one has 1 3, this one has 0. Same thing, I can write this 3 to the power of 0. This is the one that has a common. And this maybe reminds you of something that we've seen with the sets and the multi-sets, so power sets, multi-sets. And when we have this to be to the power of 0, or 3 to the power of 0 is going to be what? Is going to be 1, right? So we can just also either we write it or we ignore it. That's going to be actually the same, correct? 4 times 5 is equal to 20. What are you talking about? No, it's 4 times 5 equal to 20. I'm not sure that what we're talking about. The common between 120 and 500. Oh, okay, I get it. Yes. So because I did not finish, because here we have 3. There's 1 3 here. There's 0 3 here. That means the 0 is going to be the minimum. So that means basically we can write 2 to the power 3 or to the power of 0, or we can just omit it, because 3 to the power of 0, any number to the power of 0 is going to be 1, which is not going to affect the change. And then what about here? We have 5. I have 1 5 here, and I have 3 5s there. So that means what do they have in common? It's just 1 5. And this is why you write, you say this is 2 times 2 to the power of 2. That means this is 4 times 5, which is going to be the 20. This is the greatest common divisor. So this is actually the method that I used initially. That was actually I was a little bit faster. This is the first method that I was using. So when we do that, what we're doing, we're looking for the minimum, basically. If the minimum is 0, I can write it like here, or I don't need to. It's going to stay 0 anyways. So that's the idea. Any questions? I'm not having any bips because the last part for today, inshallah, and it looks like probably we're going to finish before Maghrib again. I hope, but this is not going to be like the all the time, but it looks like this time is going to be possible. But yeah, let me ask you this maybe. Can we start a little bit earlier, or does some of you have any courses that, for example, if we say not because Asr is becoming to be early, that means if we can, let me ask you this, like as a, okay, let me just try to share a poll. Wait, just can we start, because if we start at 3 for example, this might give us some time. Can we start the lecture at 3 p.m. instead of 3:30? But I'm not sure that this is going to be actually possible for everyone, but at least for those who are here, I think so many people are missing, but at least I can have an idea about what's going on. Well, 3:15 is not going to be. I mean, 3:15, 3:30 is not going to be a big difference. But something is better than nothing. We can check that. But at least let's see for 3:30. At least for 3. So we have 13 people saying no. Okay. Okay, because you have some classes or something. Okay, so fine. Let's keep it at 3:30. We'll take the break after for Maghrib, and then we come back, because now the Maghrib is going to come back and go to 4:45 and so on. Anyways, we'll continue as it is, inshallah. But actually, for today, we're not going to be having plenty of thing. Okay. What is this? Keep going. Oh, I'm doing it. So, okay, let's go back. Somebody was saying something. I was able to review my paper at the college. Okay, that's another story. Send the email about it, because, or maybe we can talk about it later. Yeah, but it was there for 3 days, so I think. Anyways, we'll talk about it. Just send me an email, and we'll see how we can, if we can, deal with it, inshallah. Now, similar to the greatest common divisor, now this is the least common multiple. So the least common multiple is a positive integer that is, if we have like 2 positive integers, a and b, that smallest possible is going to be the smallest one that can divide both a and b. And now we're looking for the least and not the greatest, so that's what we're going to be looking at. So if we're doing something, let's say, I don't want to introduce this, talk about the max. Let's have a look at here, for example. Now, what's the, if we have these 2 numbers, what's the least common multiple for that? So basically what we're looking for the number that is going to be the least one dividing the 2. Now have a look at this. This is going to be, what is these numbers? I mean, if we just try to expand the numbers just to have an idea, 2 times, this is 8. I mean, this is kind of a big number. It's not going to be easy to follow. But let's try with maybe another number that's going to be much easier, but I cannot find it. Okay, maybe I didn't do the exercise. This is the Euclidean. That's something else. Okay, I thought I included an example of that. But anyways, let's take some numbers. Okay, if I have the let's say I have 12 and 36. So I would like to have the least common multiple of A and B. So basically what we're looking for is going to the list of the primes, like this one, and then going for the maximum of the two if they are in both of them. So instead of the minimum that we were doing with the greatest common divisor, this is the least common multiple, because now we're looking for the multiple, and this is going to be equal to what? 2, because 12 divided by 2, so it's going 2 times 6. 6 divided by 2, so that means we have 3. So 2 to the power of 2 multiplied by 3. What about 36? 36, if you divide by 2, is going to be and then 36 divided by 2, 18, right? 18 divided by 2, that's 9. So it's going to be 2 square, that's 9. And then 9 divided by 2 I can't, so it's going to be divided by 3. That's 3. And that's going to be like this. So now, if I have this here, what the least common multiple of 12 and 36 is going to be, I have 2 in both cases. Okay, so what's the maximum of these two? Well, in this case both of them have 2, so I'm going to be 2 square times, I have 3, one that has 1 here and one that has 2, so it's going to be 2. So what does this mean? The least common multiple is going to be 36. Somebody has a question? No? So basically what we were doing here with the minimums, with the greatest common divisor, we are doing now the same for the least common multiple. So we're looking for the prime factorization, and then instead of looking for the minimum, we just look for the maximum, and this gives us that result. So if we now have a look at this and these two, and we try to look for the least common multiple of these two, so what is going to have, we'll be having that's between the 2 to the power of 3 and 2 to the power of 4, so that's going to be 2 to the power of 4. Between 3 to the power of 5 and 3 to the power of 3, there is going to be 3 to the power of 5. And then between the 7 to the power of 2 and there's nothing. If there's nothing, that means there's a 7 to the power of 0. So which one we're going to take? So it's 7 to the power of 2. So this is going to be the least common multiple. And notice that this number is basically this one here. That's this one times 2. So that's the idea, because you have this one here is 2 times 3, this one 2 times 4, everything else is the same, so we just multiply 2 by that anyways, but that has nothing to do, this is just a coincidence in this case. Now let me finish with this Euclidean algorithm, which is an algorithm how to find the greatest common divisor. And let me just jump into this here. Find the greatest common divisor between these two numbers using this Euclidean algorithm. So the idea is that we do successive use of the division by taking this and we divide this one by the other one. Generally we take the biggest one and we divide by the smaller one, and we see how many we're going to get. And you can see that, for example, this here 662, let me just try maybe just to highlight. see here, this 662 is going to be divided by the smallest number, and then that smallest number again, this is the one that is going to be divided. So what we do is basically we're keep taking this and try to divide it without having the remainder. Now this remainder, once we have it, we're going to be dividing the smallest number with that remainder. Let me just maybe again change. This is the remainder. This is the one that's going to be now the one I'm dividing by. And basically all I'm doing is I'm doing just this now I need a third color. Okay, so this one I'm going to be dividing it, so let's say 662. This is going to be equal to 414 plus multiplied by 1 because I'm trying to divide by some number that is going to make it with the remainder. The remainder obviously should be smaller than this, what I'm dividing with, this here. So that's, I cannot multiply by 2 because that's not going to be possible. So the 1 is going to be the other one. And then what I'm doing is that, again, I'm taking 414 is going to be equal to this remainder, and then try to multiply it by 1. What is going to be remaining after I take 248, I remove it from 414. This is going to be, maybe let me write it this way, minus 248. So this is going to be this 166, this here over here. And then I take again this 248, and I'm going to take 166 and remove this from it. So it's going to be 82, and I keep going it until I actually have this remainder of 0. Once I have that, so when a 0 remainder is reached, we take the last non-zero remainder to be the greatest common divisor. So that's going to be this 2. After we find the 0, we just go back one step before and then find out this is the greatest common divisor. So let's have a look at maybe another example. Now it works nice when we have like these kind of big numbers, so it allows us to actually do some kind of iterations. So if we take this 54 and 888. So what we are going to do is start with the biggest number equal to 54 and try to divide it and get some remainder. So let's divide this. Hold on, where did I put my calculator? So let's have this 888. Then I'm going to divide by 54. So it's going to be 16 point something. So basically what I'm going to do is have this is going to be 16 plus, now all I have to find out is this point something is going to be, let's remove 16 and then this point, this multiplied by 54, so I can know what it is. So it's going to be this plus 24. Now what I'm going to do is I'm going to get this 24 now and try to get how many 24s I'm going to have in it. So obviously I can divide by 2, that's going to be 48, and then all I have to have this 48 plus 6 is going to give me this here. So this is actually where the 6 comes from. And then I keep going, so this one now is going to become the number that I need to divide by 6. So this 6, that's actually 6 times 4 is going to be 24, so the remainder is 0. Now that I have the remainder 0, I'm going to stop and just go back to take the previous remainder and say, oh, now this greatest common divisor between the two, the greatest common divisor between these two numbers is going to be this 6 here. So it's kind of like a formula to be able to find it, kind of straightforward. But of course you have to not get confused, especially if you're doing, for example, this type of big numbers. Now all you have to do is to type this divided by, but actually this is not so much of a big issue, because if you divide by these two numbers, this one divided by 7 is going to give you this point something, and then this point something, you just write it as the remainder, and that remainder is the thing that you're going to divide whatever you divided first by it, and then you keep doing it until you find that your remainder is 0. The one before is going to be your I think there's a mistake here. This here should be 7 and 876543. That is what is meant. So that's the that is the Euclidean algorithm. Now we have some cup of time before the Maghrib. I don't know if you have any questions. You seem too quiet to, I don't know. Now determine if one of these integers is a prime. Okay, let's have a look at maybe let's take this one. 111. Is this a prime? Let's try this one because it's fairly big enough. Or maybe let's take this in the middle, the C, 71. Is 71 a prime? Now to know that, remember what we have to do? Check the primes. If you can find that there are no primes that are going to be less than this number. Okay, what is that number? Okay, I need to find out. So 71, and do the square root of that. So this is going to be 8.42. That means, well, 8 point something. So I need to find a number that is less than 8. Well, I know that the primes are going to be 2, 3, 5, and 7, because these are the ones that are going to be less than 8. So now, let's find out. 71, does it divide 2? No. How about 3? Well, 7 plus 1 is going to give me 8. That's not a multiple of 3, so it's not going to divide 3. Does it divide 5? No. How about 71? Does it divide 7? Well, no, because 70 would divide 7, 71 doesn't. So I'm pretty sure now that 71 is going to be a prime. And we just listed the list of all primes, so you can go back to that. And 71 is one of them. So this square root thing is very convenient. It allows us to actually, okay, debug again. And now find the prime factorization of each of these integers. So we can maybe pick one number that is kind of, we did some of these, and we might take this. Let's start with this 126. Again, debug. Cancel. Can I cancel? All right. So 126, what are the prime factorization of that? So I just divide by 2. That means 2 times 63. So I'm going to divide by 2 more. So that means it's going to be 3. Can I divide by 3? 6 plus 3, that's 9. Well, yes, I can divide by 3. So what I'm going to do is 63 divided by 3 is going to be what? 63 divided by 3 is going to be 2 times 3 times 21, right? 3 times 1, that's 3. 3 times 2, that's 6. That's 63. Okay. So this is also, I keep divide by 3 again. So this can be divided by 3. So this is going to be 2 times 3 times 3 times 7, because 7 times 3, that's 21. So this is going to be 2, 3 square 7. This is the prime factorization of that integer. Okay, we can move on. We can have a look at this. I mean, this thing, I mean, you can have the solution. I'm leaving it for you so you can practice that. Basically, which positive less than 30 are relatively prime to 30. This is actually, the idea is relatively prime if they have this greatest common divisor. So you have to use, I'll just leave these so you can know what we're talking about. So again, we'll determine whether these are pairwise relatively prime, which means I have to find the greatest common divisor between 11 and 15, then between 15 and 19, then between 11 and 19. So I'll just check this one, these two, and all of them. This is the, and if all the three should be equal to 1, then I can say that yes they are, or no they aren't. And here these are like two numbers. I would like you to find the, I mean, I could have also used this same exercise to find the least common multiple and the greatest common divisor, both of them. So for this I'm going to use the max, for this I'm going to use the min. So I'm just going to look at what is the in common between the two, and then use the max if I'm looking for this, the least common multiple of 3 to the power of 7. Let me just maybe write it a little bit better. LCM of 3, 7 times 5 to the power of 3, 7 to the power of 3, and then 2 to the power of 11 times 3 to the power of 5 times 5 to the power of 9. So remember, for this least common multiple, I need to find the maximum. So 2 here is 0 on the left side, on the right side is 11, the biggest is going to be 2 to the power of 11. What about 3? 3 to the power of 7, 3 to the power of 5, then I'm going to make 3 to the power of 7. And then what about, we have 3, yeah, right? And then we have 5 to the power of 3 here, and then 5 to the power of 9 here. That means I'm going to be having 5 to the power of 9. I have 7 here, and I have 7, and I don't have 7 on the right side. That means if I don't have 7, it's equivalent to have 7 to the power of 0, which means, because I'm looking for the least common multiple, I'm looking for the maximum, and I'm going to make this to be the least common multiple. And if I was to use this now for the greatest common divisor of these two, so I'm going to look now for the minimum. So here, for example, I'm just going to, they have 0 2s and they have 11 of them, so I'm not going to take any one. The minimum is the one with 0, so I'm not going to write the 0, or I could put 2 to the power of 0, which is 1. And then for the 3s, I have 5 here, 7 there, so I'm just going to use 3 to the power of 5. And then I used 5, okay, 5, I did not use it yet, so 5 to the power of 3, 5 to the power of 9, so I'm just going to use the minimum, so 5 to the power of 3. And then 7 here to the power of 3, and then there is no 7 here, so that means power of 0, that means I'm going to make 7 to the power of 0. So in other words, it's 3 to the power of 5, 5 to the power of 3. That's the greatest common divisor. Well, I'll let you, I spent some time just to make these animations for you, so you can test yourself, you can practice before going and seeing the answers right after one after the other, so you can just try yourself. And so there's no need for you to, you can do that, I mean, but you can just practice. Now also you can use this Euclidean algorithm to find the greatest common divisor. Let's start with these two, and then we stop here, inshallah. And oh, I just realized the Maghrib time has already entered. So let's do this quickly. Okay, so we have this 12, 18, the common. So what I'm going to do, I'm just going to find this here, 12, the biggest one. I'm going to divide this by the 1, so it's going to be 1 plus what? So plus is going to be 6, right? And then this 12 is going to be equal to 6 divided by 2 plus 0. So now that I found 0, I'm not going to look at this. I'll go back up and see that this is going to be equal to 6. That's pretty much what I have for you for today. So if you don't have any questions, you're free to go. For those who have questions about what I read regarding the copies, you did not have time to check them. Anyways. I just send me an email, and then I'm going to reply to the email, inshallah. So if you don't have any questions, inshallah, see you next week, bismillah. Okay, for the email, I'll check it, inshallah. Yeah, if you have a question, please ask your question now. If you don't, you're free to go. Assalamu alaikum. Okay, assalamu alaikum.